So let's take a look at the next combination of acid and base and see if that one will form a buffer. And here's a combination of a weak acid and conjugate base. So we'll try to pick up example of a weak acid, but we can generically say that it's called HA and it's going to dissociate into H plus and A minus. The difference between this and something like HCl is that the Ka of a weak acid is very small, and therefore what we will see at equilibrium is not the proton and the conjugate base. What we would see is just mostly the HAs. You can say that 99% of the particles that exist in solution is HA, with a small percentage being the H plus and A minus. The conjugate base solution of a weak acid is just a solution that has A minus in it, and we'll talk about how we can generate that. But if you just have A minus in solution, by definition, the conjugate base of a weak acid is going to be a weak base, because we can calculate the Kb of that weak base is just going to be using that Kw over Ka of the HA, right? And as a result, you can see that if the HA is small, Kw is 10 to the minus 14, your Kb is going to be smaller than 1 as well. So your A minus is going to be a weak base, which again implies that in the reaction of A minus with water that we have in the aqueous solution, we're going to make some products, but it'd be very, very little. Most of our solution will just be A minus. So again, think about what happens now. What you have in your solution is mostly HA and mostly A minus, just floating around there. The next question we're going to ask is there a reaction between the main acid and base species that exists? Well, the main acid species is HA, the main base species is A minus, so they're just conjugate acid-base pairs. So if I put them together in a reaction, all I'm going to get is the same thing. So that just means that there's no reaction. So in conclusion, what do I have in my beaker when I put a weak acid and its conjugate base? I'm going to have mostly HA, which is the weak acid. I'm going to have mostly A minus, which is the conjugate base, which happens to be a weak base in this case. Now, this will make an excellent buffer. Why? Because we have the two components that we're looking for that will help neutralize any additional acid and base. So if I add H plus to the solution, the A minus, which is the base, is going to be able to neutralize that incoming H plus. If I add OH minus to the solution, the HA that I have is going to be able to neutralize that incoming OH minus. So in other words, I have the two components I need in my solution that would neutralize any incoming acid or base. Again, compare this to that strong acid, strong base combo that we discussed earlier. In that solution, all we have at the end is just water and some neutral ion. So nothing in that solution will help us neutralize any incoming acid or base. In this current solution, the weak acid and its conjugate base, we have the two things that we need to neutralize the addition of acids and base. So this, therefore, will work as an effective buffer. We can make it like that. So what is an example of this? You can come up with your weak acid HF, for example, and then you can mix that with F minus, which is a conjugate base. Now the question becomes, how are we going to generate just the F minus solution? Again, we're not going to be able to generate enough F minus by putting HF in there, because the HF doesn't dissociate enough to generate a huge quantity of F minus, right? So where should this F minus source come from? If you recall, we can't just put F minus. Ions don't exist on their own, right? They always exist as a compound. So if you want to make somewhat equal quantities of HF and F minus, the F minus has to come from another source, and that source has to be some type of a soluble salt that will dissociate to release that F minus or any conjugate base into the solution. So for example, a buffer you can make would be a combination of HF and NaF, or sodium fluoride. The sodium fluoride is soluble salt, so when you put it in water, all it will do is split up, dissociate into sodium and fluoride ion. Now we have both the HF and we also have the fluoride ion, and they both serve as the buffer, okay? And you can come up with other examples of this. For example, if you have carbonic acid and its conjugate base would be a bicarbonate ion, but again, can't come with bicarbonate on its own, so I can find a sodium salt of bicarbonate, so Na bicarbonate or sodium bicarbonate. These two would then make a buffer solution. Now let's talk about our next combination that's possible, which is a weak base and its conjugate acid. This idea is really the same as the previous one, where we just talk about weak acid and its conjugate base, except that now we're starting with a base. So weak base, for example, any of those ammonia derivatives that we talked about before, could be a weak base. And a weak base is going to react in water to produce the conjugate acid and OH minus. But again, remember that by definition, because it's a weak base, the K value is small. We call this Kb. And so most of the species is going to remain as B. Again, so B would be the major species in the flask or in the solution. If I'm able to find a source of my conjugate acid, by definition, the conjugate acid is going to be a weak acid. I know that because I can calculate the Ka of my conjugate acid by taking Kw over Kb of my base. And again, similar logic like the acid case, this is going to be a small K value, which means that the Ka is small. It's a weak acid, so most of it would just remain on the left side of the reaction. So what do I have in my solution? I'm going to have the following species. I'm going to have some base and I'm going to have some conjugate acid. Will that work as a buffer? Absolutely, because I have the two things I need to neutralize any incoming H plus and OH minus. So if H plus is coming in, the base is going to neutralize it, okay? And if hydroxide is coming in, the conjugate acid would neutralize. So in both cases, we're going to not have a big change in pH because there are components in that solution that would help neutralize any strong acid or strong base. So what is an example of a buffer that looks like this? Well, you can pick any weak base that you know of. We learned a few of them in the previous chapter, but most of them are derivatives of ammonia. So I'm just going to use ammonia here as my weak base. And the conjugate acid of ammonia is the ammonium ion. Okay, NH4 plus. When you have the ammonium ion, there has to be a counter ion that neutralizes that positive charge. So for example, you can mix ammonia with ammonium chloride. The ammonium chloride is a soluble salt. It will dissociate completely to form ammonium and chloride ion. The ammonium is what matters to the function of the buffer. So you're going to need the ammonium and the ammonia. Then what does the chloride ion do in this case? It doesn't do anything. It's just a spectator ion for the purpose of the buffer acid-base reaction. Now let's take a look at the next combination, which is a combination of a weak acid and a strong base. So notice the difference between this and part B earlier where I'm taking a weak acid and I mix it with its conjugate base solution. Right now I have a weak acid and a strong base. So what's some example of this? I can pick any weak acid I want, right? HF, HCN. So I'm just going to use HA to represent this. The same way as we rationalized it earlier, if it's a weak acid, that means that most of the species that exist would be the HA itself, since the Ka for this reaction is small. The strong base, on the other hand, for example, NaOH, will dissociate completely. That is by definition what strong bases do. So we have Na plus and OH minus as our major species. This is what we have in solution at equilibrium for these mixture. We're going to have HA, we're going to have Na plus, we're going to have OH minus. Now remember our second question that we have to ask, if we have these three species, is there any two of them that will react to a significant extent? And again, that means that is there any of these guys that would react with a large K value? So there's some combination, there's HA, Na plus, and OH minus. So we just have to ask ourselves, which two of these three things we're going to react with each other? Will HA and Na plus react with each other? The answer is no. Na plus is a neutral ion, HA is an acid. There's no reason for those guys to react with each other. What about HA with OH minus? Well, here there's going to be a reaction because HA is an acid, OH minus is a base, so you're going to form water and A minus as the other product. And then we're going to see whether that's something we need to worry about or not in a sec. What about Na plus and OH minus forming NaOH? Well, again, this is not a reaction we have to worry about too much because the strong base is going to dissociate. So the reaction is actually much preferred to form these two species than the NaOH. So then we don't need to worry about the back reaction to form NaOH. But what about this reaction that I wrote here, the HA plus OH minus going to water and A minus? If you look at that reaction, I'm going to write it right here just so that you can see it better. It's actually the reverse of a weak base reaction with water, right? And hopefully you can see that when we have weak bases, we would say the weak base will react with water to form its conjugate acid and OH minus. This is just the reverse. Now, what I care about here is finding out what the K of the reverse of a weak base reaction. That means it's going to be the reciprocal of whatever the K is for the weak base reaction with water. But that K we call Kb, right? So Kb values are much, much smaller than 1. So therefore, 1 over that number is going to be a reaction that has a much larger than 1 K value. So in other words, at equilibrium, this reaction will end up producing a lot of A minus. So the reaction will go to completion, okay? So these two is going to produce that and water. What you might say at this point is like, well, okay, so then I'm not going to have a buffer. All I have in my solution, if I think about what happens here, all I have in my solution is Na plus, right? That's one of the ions. OH minus react with HA, so I'm going to have A minus. So all I have is Na plus and A minus. A minus is a base. Na plus is neutral, so there's no acid here. And because there's no acid, I can't really neutralize any incoming base. So therefore, this is not going to work as a buffer. That's true only if the HA is completely consumed by the OH minus, right? Think about that a little. If you have equal concentrations or equal number of moles of HA and OH minus, you're absolutely right. Both of them will completely react, and all we have in the solution is A minus. But let's say the OH minus is a smaller amount, a limiting quantity, okay? Let's say you only have 5 moles of this and you have 10 moles of that. Well, the reaction will then consume 5 moles of the HA and it will produce 5 moles of this at the end, right? That would be completely gone. But this will still have 5 left. So if we have 5 moles of HA and 5 moles of A minus, that means we have 2 things that will neutralize any incoming acids or bases, which means we have a buffer. So in other words, it will work as a buffer, but you just have to be a little careful with how much acid and base is present. So for a mixture of weak acid and strong base to make a buffer, we're going to have to make sure that the concentration of the weak acid initially, which is HA naught, has to be greater than the concentration of hydroxide initially, okay? So this part here has to be followed to make sure that we have a buffer present at the end. So again, when you're mixing a weak acid and strong base, you may make a buffer or you may not. It depends on how much acid and how much weak acid and how much strong base you start. So you need to do a little calculation. You can't just say that I'm going to get a buffer or I'm not going to get a buffer. Last combination, it's a weak base and strong acid. So the logic here is similar to the one that we discussed about the weak acid and strong base. The weak base is going to end up just staying as weak base because the Kb is small. So that will be one species we have. The strong acid will split up and it will make the H plus and Cl minus in solution, right? So an example is HCl here. So again, we have 3 different species that are highlighted in yellow. The question is, which 2 of those species will react with each other? And just going through the same logic that as I did earlier at the top, the only reaction that will happen to an appreciable extent is the reaction between H plus and B. So H plus is our proton that comes from the HCl. The B is the weak base that was originally there. And they're going to form the conjugate acid of the weak base, which is BH plus. This K is going to be a large K, because it's 1 over Ka. So again, at the end, at equilibrium, what am I going to have? I'm going to have some Cl minus, that's neutral ion, and then I'm going to have BH plus. But it depends on the relative quantity of H plus and B. If we have a lot of B to begin with, and the H plus is the limiting reactant, then at equilibrium, we would also have some B present. And since we have BH plus and B both, we have the 2 components we need to neutralize any incoming acids and base so we can have a buffer. So again, for this one, same conclusion like the previous one. If we want a mixture of weak acid and strong base to make a buffer, we must have more B than H plus initially. So the concentration of the weak base initially has to be greater than the concentration of the strong acid initially, the H plus. So the example here is you can make a buffer if you mix 10 moles of ammonia and 5 moles of HCl. You're not going to have a buffer if you make 10 moles of ammonia and 10 moles of HCl, because then it will just get neutralized and all you have at the end is the conjugate acid. Okay, so let's draw some conclusion here. We will get a buffer if at equilibrium our mixture has 2 things in it: a weak acid's conjugate base, HA and A minus, or a base and its conjugate acid. So if you look through the 4 cases out of the 5 that we discussed, the ones that can make buffer all have those, either a weak acid and its conjugate base or a weak base and its conjugate acid.